All right, guys, so today we're going to talk about curve sketching. It basically takes everything that we had been talking about with finding our maxes and mins when my function's increasing, decreasing, concavity, and it puts it all together into one section. So whenever you're going to look at a graph and you're going to do anything with curve sketching, there's a couple things I want you to do. There's a couple steps to follow. So the first thing you want to do is you want to figure out what the domain is of the function. You want to find that first. And after you find that, that's going to determine where you need to be concerned about the values of the function. Second thing you're going to do is you're going to go back to and remember all of those strategies you had in pre-calculus, and you're going to find x-intercepts, asymptotes, and symmetry. So if it has any of those things, you want to know about it before you get started on that. So you're going to find the intercepts, the x and the y axis. You're going to see if there's any symmetry. Remember how you did that by plugging in negative x to see if it was an odd function or if it was an even function. You're going to find any asymptotes that it may have. Remember, that's where the function's undefined, so you set the denominator equal to 0 and solve it. And finally, you're going to look at the derivative and the second derivative to find where your function is increasing, where it's decreasing, where any max and minimum values occur. You'll look at the second derivative to talk about concavity. Is it concave up? Is it concave down? And any points of inflection. You want to do all of these things before you graph any function. I'm going to show you a couple examples of what this may look like. So here's the first equation we're going to take a look at, 3 times the quantity of x squared minus 4, that whole thing over x squared minus 9. So there's really no purpose in multiplying out the top, although you could come up with 3x squared minus 12. It's not going to help you out in this problem whatsoever, though. So again, remembering those steps that we're going to go through, the first thing we want to figure out is we want to figure out what the domain of the problem is. So the domain, remember, with any rational equation, the denominator can't equal 0. So the domain for this problem, x cannot equal plus or minus 3. We always like to talk about the range, but I'm just going to leave that blank for now because I don't know what the range of this function is until I graph it. So I'm just going to hold off on filling that part in for now. So that's the first thing I want to find, the domain and the range. The second thing, let's take a look at the x-intercepts and figure out if this graph has any x-intercepts. If you remember to find x-intercepts, we set my function equal to 0 and I solve it. So that's basically when the top's equal to 0. So you get x equals plus or minus 2 for that particular function for the x-intercepts. And the y-intercepts, we can do those as well. The y-intercepts, we plug in 0 into my equation. That's where maybe multiplying it out might be a little bit easier because we do end up with this fraction negative 12 over negative 9. So my y-intercept is going to be at 4/3 when I simplify down that fraction. That's going to be a helpful piece of information for me to know. Next, we want to look at any asymptotes that my function may have. If it's not a rational equation, of course I wouldn't have any. But because this is a rational equation, I do have 2 asymptotes. And remember, they're going to be the same as your domain values like you've talked about before. So at x equals 3 and x equals negative 3. I should figure out, by the way, these would be my vertical asymptotes. So I should label that so I don't get myself confused. Horizontal asymptotes. Okay, now remember, this was that last section that we talked about limits towards infinity, where we're taking a look at my function and I'm evaluating the limit as this approaches positive infinity, as well as the limit as this approaches negative infinity. In this case, we could also, because it's a nice rational equation that we remember from pre-calculus, we can use those rules that says since the degree on the top is the same as the degree on the bottom, then I come up with the horizontal asymptote at y equals 3. So those are rules that we had already known. There's no need to actually evaluate the limit in this particular problem, although if we did, this is the answer that we would come up with. So it's worth taking a look at that. Symmetry would be the last thing I want to take a look at before I do anything with my derivative. So remember, for symmetry, what I'm going to do is I'm going to plug in negative x. Let me do the work of that over here. So 3, and then I have negative x, that quantity squared, minus 4. And on the bottom, I'd have negative x squared minus 9. And if I know this, a negative squared gives me a positive, so that turns out to be exactly the same thing as it was on the top. And on the bottom, negative x squared, that's a positive. I get the same thing I have on the bottom. So what I end up with is a situation where f of negative x is equal to f of x. Because of that, I know there's symmetry across the y-axis, and my function is even. Okay? Or if I want to say about the y-axis, that's okay too. I can say that with this particular function. I'm going to take a minute right now and we'll put all of this onto my coordinate plane so we can see what we have so far. So let me plot this. The my asymptotes, I'll put my asymptotes in. I'll put my other asymptote in. I'll plot my y-intercept, which is, we'll call it right there. I'll apply my x-intercepts there and there. And that's basically all. Oh, the horizontal asymptote. Let me put that in there yet. So far, this is the graph that I have of my function. That's all I can figure out from the equation itself. Now I have to go to step 3, which was to take a look at the first derivative and the second derivative and talk about where my function is increasing and where it is decreasing. So let's take a look at the derivative of x. This is definitely a case where you're going to have to do the quotient rule because I have a function here on the top. Maybe I'll take a look at this. I was reluctant to do it before because it wasn't really going to help me, but now with my derivative it might. I'll multiply out that top. So remember the quotient rule, bottom times the derivative of the top plus the top times, minus the top times the derivative of the bottom all over the bottom squared. So it's the bottom times the derivative of the top. Let's see here, that'll be 6x minus the top times the derivative of the bottom all over the bottom squared. I'll simplify that. I'm going to save you the algebra of me simplifying that, and I'll tell you it'll simplify down to negative 30x over x squared minus 9, that quantity squared. That will be the value of my first derivative. Now, remember to figure out where my function is increasing or decreasing, where the max and mins are. I set my first derivative equal to 0, and I solve it to look for all those critical values. Where the top is equal to 0, I'll come up with x equals 0. Where the bottom is undefined, I come up with x equals plus or minus 3. That didn't change. Actually, that's really interesting. That's part of the domain values there as well. But I still have to consider it because it's going to be a change in whether my function's increasing or not. So I'll look at this on a number line, just like I did before. Remember to label this as f prime of x. This, when we look at the big problem, it'll be less confusing that way for you. I'll test a value. So I'll put in a number less than negative 3. I'll put it into my first derivative. When I put that in there, the bottom's always positive. So it's really the top that's going to affect my sign. So I'll plug in like negative 4. That gives me a positive number on the top. I'll plug in negative 2. Again, a positive number on top. I plug in a positive like 1. That'll give me a negative value on the top. I'll plug in positive 4. That'll give me a negative number on top. So from this, what I can tell is I can tell that my function is increasing from negative infinity to negative 3, and from negative 3 to 0. Now, if you remember that problem that we did in class the other day, when we were talking about my function increasing or decreasing, we didn't break it up into 2 parts when we had that different critical value. I am, however, going to break it into 2 parts here because remember, at negative 3, I have an asymptote. So I have to consider that when I'm going through the problem. My function is decreasing on the interval from 0 to 3 and from 3 to infinity. And again, I'm making that break because I have an asymptote at positive 3. So if I look at this, really the only thing where I'm changing from positive to negative is from here to here. So I was going from increasing to decreasing, which means right there at 0, I'm going to have a maximum value. So I know that I also have a max at 0. And to figure out what that value is, I go back up to my original. Oh, wait, hey, I already did that. It's my y-intercept, 4/3. I'll now add this information to my graph, or at least consider this when I'm going through my graph. My max is already plotted, so I have that right there already. Just know that's going to be a maximum value. I'm almost done. I'm almost done. This is a big clue as to what's going on. So I know my function is, when I go from negative infinity to negative 3, it's increasing. Well, it can't go here because that would give me an x-intercept. So it's going to go here, which means it's going to have to go like this, or it could be going like this. Now, that really doesn't make any sense, but I want to check myself with concavity just to make sure. Just to make sure. So let's check out the second derivative. So if that's the first derivative, I want to keep that there. That's the first derivative. To take the second derivative, again, I have a nice quotient rule that I'm going to have to deal with. So the bottom times the derivative of the top minus the top times the derivative of the bottom. Uh-oh. Don't forget chain rule here, people. Don't forget chain rule. It'll get you if you're not careful. That whole thing all over the bottom squared. Now, I'm going to, that squared. So I'll do a little simplification for us, because again, I'll save you the algebra. I'll tell you what it is for the second derivative. And the second derivative, when you simplify that down, you'll get 90 times the quantity of x squared plus 3 all over x squared minus 9 to the fourth power. Sorry, to the third power. So we'll take a look again at these values. So I look at the top, and when's the top going to be equal to 0? Well, the answer to that is never. Because if I set this, I'll divide that by 90. That 90 we can disregard. But if I set that, that'll be x squared equals negative 3. And I can't square a positive value and get a negative one. So that doesn't work. I'll never get any values there. So when I'm taking a look at then, really the only values I have to consider is that x cannot equal plus or minus 3, which again, they're the asymptotes that popped up a second time. So when I'm looking at my number line here, f double prime of x, and I put the values of 3 and negative 3 on it, again, I'll test my intervals. I'll put a number negative 3. And well, the top's always positive. So it's really the bottom that's going to determine my sign. So when I put in like a negative 4, negative 4 squared gives me a number that's bigger than 9. I'll get a positive value on the bottom. But when I put in 0, something that's in this interval, 0 squared is 0 minus 9 is negative 9. Negative 9 to the third power is a negative value. So that's negative. And then when I put a number bigger than 3, that turns into a positive number. So again, when I'm talking and looking at my function, I know now a little bit more. I know that, let me erase this. I know that I'm going to be concave up from negative infinity to negative 3. And from 3 to infinity, I'm concave up. And I'm concave down from negative 3 to 3. Now this is an interesting point where I would say, hey, don't I have a point of inflection at negative 3 and positive 3? And the answer is I don't, not in this problem, because that's the asymptote, and that's another asymptote. So I can't have a point of inflection at an asymptote. But I will notice a change in concavity there. So we're tying it all together now. We're going to put it all together. All that information about where my function's increasing, where it's decreasing, I'm now going to put on my graph. So if I remember from the problem that I just did, from the work that I had there, I know that my function from negative infinity to positive 3 is increasing. And based upon what I just said about concavity, it is also concave up. So concave up is a smiley face. So I got a smiley face going from negative infinity to positive 3, and it's an increasing smiley face. So what I know is I got a function that's going to look a little bit like that right there. Because of symmetry, because my function is even, I know that this has to be the same thing over here but going the other way. And this also makes sense to me, because if you remember from what we just found out, my function from 3 to infinity is concave up again, smiley face, but my function is decreasing. So I have that going on here in this particular part of the problem. Then, again, from my first derivative, I saw that from negative 3 to 0, my function was increasing. And then from 0 to 3, my function was decreasing. And it is concave down on that entire interval, so frowny face. So let's see here. That means frowny face. And I have my function graphed as accurately as I possibly can do it without plotting an infinite number of points and using all of the information from calculus to help me do this problem. Guys, before we go into the next problem, I forgot to talk about the range. I didn't fill that here in with my problem. So we want to consider the smallest value to the largest value. And if you look here, negative infinity would of course be the lowest value because my function keeps going on forever down. But then if I look, where do I stop? I stop here at 4/3. I have this break, then I go from 3 to positive infinity. So where's that happen? Remember, that happens at the maximum value, which we already found. We found that when we did our first derivative. It also happened to be our y-intercept. So my range is going to start at negative infinity, and it's going to go to 4/3. Because that is a maximum point, we include the 4/3 in that interval. And then it stops, and I have this break in my function. It gets to 3. But remember, that's a horizontal asymptote, and my graph doesn't cross this horizontal asymptote. If it would, then I would find it as a relative minimum value somewhere on that curve, and it doesn't have that. So I will go to 3 to infinity. I almost forgot the range. I'm glad I didn't. Okay, so here's the second example problem we're going to do, and I'm going to not quite go as in depth, rather go through it a little bit quicker. The function g of x equals x over the square root of x squared plus 2. So the domain, I don't have any undefined values here. This is always positive, and it can never equal 0. So my domain is going to be negative infinity to positive infinity. We'll come back and fill in the range, and I promise I won't forget about it this time. The x-intercept, when I made y equal to 0 and solved it, I came up with x equals 0. The y-intercept, when I plug 0 into my equation, I come up with a y value of 0. Vertical asymptotes, the bottom is never undefined, so there aren't any vertical asymptotes. There are also no slant asymptotes, not something that we could find with this particular problem. But let's spend some time talking about the horizontal asymptotes. This is just the lesson that we just did last class period. So what we have to do to evaluate and figure out if we have any horizontal asymptotes here is we have to look at the limit as x approaches infinity of my function. If you remember correctly, we had this rule that says we can only evaluate the limit if x is on the bottom of the fraction. It's a constant over x to any power ends up being 0 as the limit approaches infinity. So what I'm going to do is I'm going to set it up exactly the way we had done on our homework. So I'll multiply by that form, 1 over x. Oh, but remember, 1 over x doesn't work here. So we have to multiply that by the square root of x squared. Remember that was the trick that we kind of were able to do the math underneath that radical sign. So when I do that, I end up with the limit as x approaches infinity. On the top, I end up with the number 1. On the bottom, I end up with the square root of 1 plus 2 over x squared. So as I'm looking at this, and I actually plug in my infinity and think about what's going to happen, the 1, of course, stays the 1. The 2 over x squared is 0. So I have the square root of 1 plus 0, which simply simplifies down to 1. So I have a horizontal asymptote that's going to occur at x equals 1. However, in this particular function, I also have to consider what happens towards negative infinity. So I'll just make that negative sign there. But remember what that changes in my problem. Because this value was always positive, I can't talk about it in the negative direction. So I have to make that negative as well. What does that do to my limit? That makes that negative, and because that gets me a value of negative 1. So I'm going to have 2 horizontal asymptotes in this particular problem. One at positive 1 and one at negative 1. That's very important to realize and to do with this problem, which is why evaluating the limit to find horizontal asymptotes is more important than maybe following some of those rules that you think, especially when it's in this form. The last problem that was a nice polynomial over another polynomial, I didn't have to worry about it so much. But here, I do. The next thing, symmetry. Again, I just want to show you symmetry. Remember, you're plugging in negative x. You're plugging in negative x, and when you do that, you get negative x over the square root of negative x squared plus 2. Well, squaring that ends up making that positive, and it doesn't have any effect down here, but on the top, it's negative. Now, this is a little different, because if you remember, this makes this whole fraction the opposite of what the original function was. So this actually has symmetry across the origin, symmetry about the origin. Because it is an odd function, because of this. Okay, we're making headway here. So I have all of this good stuff that I've already figured out. Now we need to figure out the first derivative. Remember, all of this information I can find out by looking at the first derivative. So I'm going to do that now. I'm going to take the derivative of this. And again, I have a situation where I have the quotient rule, and I have to worry about making sure I do the chain rule as well with that. This form may not be the one that you like. Quotient rule with this is a little tricky. You could also maybe take a look at it like this, just to give you another way to look at the problem. That would be another way, and then you could do product rule instead of quotient rule. Regardless of the way that you choose it, I have my cheat sheet here where I've already figured out what the first derivative is, and I'm just going to go ahead and tell you what it is without going through it. You can do that on your own. I end up with 2 over x squared plus 2 to the 3/2 power. Okay. Remember, to figure out where this function is increasing or decreasing, I need to take a look at when this is equal to 0. Well, hold on a minute. This thing's never equal to 0. The bottom is always a positive number and can never equal 0, because if I try to take that, square it, and set it equal to -2, it never happens. And the top, there's nothing to solve for here. So guess what? When I'm looking at my graph of my function and figuring out whether this is increasing or decreasing, I don't have any numbers on it at all because there are no critical values. What does that mean for my function? Well, now I can just plug in any number my little heart desires. So I'm going to plug in 0. So that gives me a positive number on the top. That'll give me a positive number on the bottom. And a positive divided by a positive is a positive. So when is my function increasing? Well, going over here, my function is always increasing. It is never decreasing, and it has no max and no min. There's no max and no min to this problem. So I have a function here that's always increasing and has a horizontal asymptote, 2 horizontal asymptotes. Okay? Let's check the concavity of this graph. And for that, I'm going to take the second derivative. Again, this now becomes a little bit easier to deal with when I'm talking about a second derivative, especially when I change the form. And I change that form, the second derivative becomes a lot easier to find. But again, I'm just going to go ahead and cheat here. I'm going to tell you what the answer is without going through all the calculus to come up with it. You guys are good at that by now. And I get -6x. Over x plus 2 to the 5/2 power when I simplify everything down. When I'm looking at g prime of x in this particular instance, I do in fact have a critical number here for the second derivative. It's not on the bottom. That's always defined. That never equals 0. On the top, however, the value that I get is 0. So something may happen at 0 here. We're going to check out to see what it is. This bottom number is always a positive number because I'm always going to get a positive number inside. Squaring a negative will always give me a positive, plus that will still remain positive, and taking it to the 5/2 power gives me a positive number. So the bottom is always positive. So the top is -6 times whatever number I pick, and that's what's going to determine my sign. So I'll pick like -1, and a negative times a negative will give me a positive. I'll pick +1, a negative times a positive gives me a negative. So what I have here, I have at the point 0, and I got to figure out what the y value is. I have a point of inflection that's happening. So my point of inflection is at the point 0, and it's a good thing I actually already figured that out, 0, 0. My function is concave up from -infinity to 0, and it's concave down from 0 to infinity. I now have enough information to be able to graph this thing. Let me show you what the graph looks like. I have an asymptote at +1 and -1. That's where my 2 asymptotes were. I'm going to really make this pretty big. Okay, I have a point 0, 0 where I have a change, a point of inflection, as well as my x-intercept and my y-intercept. Well, man, that's all the information I have. I don't have any other information except for where my function is increasing and decreasing, and where it's concave up and concave down. So I know here, from -infinity to 0, my function is concave up, so it's a smiley face. And it's increasing. It's always increasing. So smiley face increasing looks a little like this. I have a point of inflection, which means at that point 0, 0, it now turns into a frowny face. It's now a sad face, but it's still got to be increasing. So that's going to kind of level out just a little bit, and then it's going to go again towards this asymptote. I've now graphed this function as accurately as I possibly can, given the information I have. Again, I could get more accurate if I wanted to plot more points. But that's not what this is about. This is about using all of these concepts from calculus and pulling them together to create one graph. I hope you got something out of this. I almost forgot again, the range. Range, the tricky little range. So what I know is I have a horizontal asymptote here and a horizontal asymptote there. Doesn't cross the horizontal asymptote. If it did, I would have a relative max because it would have to go down towards that asymptote again. So my range actually ends up being from -1 to +1, and that's not that bad. So I hope you guys got something out of this. You now have some homework to work on, so get to work on that. I'll see you guys next time.